So last time we were looking at sigma-algebra generated by a collection of sets, and in order to do that we proved this lemma that any family of sigma-algebras you've got at all, when you intersect them you get another sigma-algebra. So this was a really easy one to prove, and yet having proved it, we now can use it to prove surprisingly powerful results. So we got as far as we proved that lemma, and then we'd made this definition, and we'd said that we were going to find the sigma-algebra generated by a collection this way, and we'd made a couple of comments about that. And the first comment we made was note curly C, as I'll write it, is a subset of the power set of X. So P of X is a sigma-algebra on X with C containing P of X. Okay, well I said that twice. But the point is that there is at least one of these. So I'm not trying to intersect the empty family, which I haven't really addressed. You could figure out what, I mean, you could say if you intersect the empty family, you should take P of X anyway, if you're working in P of X. But we don't have to worry about any of those sorts of problems. So there is at least one collection of this family. And so now, when you intersect them all, you will get a sigma-algebra, and of course, you will get that C is a subset of it. You could write it another way. So sigma x of C is equal to the intersection of, this is set theory intersection notation. It means intersect all the things in the following collection. So it's those F contained in P of X. So it's those collections of subsets of X such that F is a sigma-algebra on X and C is a subset of F. So that's just another way, that's a way of using set theory to denote the same thing. This is the set theoretic intersection notation, which means here are a lot of things, a lot of F's here, intersect them all. So that's what this notation means. And we now know then that, so by our lemma, whichever our lemma was, it was lemma 3.9, sigma x of C is a sigma-algebra on X. And obviously, everything in C is in there because anything in C is in all of these collections. So and by the definition of it, whenever F is a sigma-algebra on X but not very good such, let's try that again. Whenever you've got any sigma-algebra on X so that everything in C is in it, so C is a subset of F, then we must have sigma x of C as a subset of it as well. So sigma-algebra C is genuinely the minimum sigma-algebra on X, which has got all the sets on C in it. I don't like to use the word containing because of the ambiguity, but it's probably the shortest way to say it. So sigma X of C really is the minimum in the sense of set partial order, sigma-algebra on X, which contains C. Containing C as a subset, as a subcollection. In fact, if I say that, it would be the clearest way of keeping track of our level. That just means subset, but I'm using collection to remind you which level we're operating at. Right, so that's very abstract, but it has given us that every collection sets will generate in this way a minimum possible sigma-algebra, which is obtained, of course, by throwing in as few sets as possible that you didn't have before, if you need them. I mean, if C is a sigma-algebra already, then of course, then you know what the sigma-algebra generates is, because if C is a sigma-algebra, then it's already a sigma-algebra, and this intersection would just be C. If C isn't a sigma-algebra, then you're going to have to throw in at least some more sets to make it into a sigma-algebra. This shows you how to throw in as few as possible, but it really doesn't tell you exactly what's in there. You can figure out quite a lot of things that are in there, and we will do that when we look at the Borel sets in a second, and we'll have a look at a lot of things that are in there that we can show. It's often rather more difficult to show that something isn't in there than it is to show that it is. How do you know that something isn't in the sigma-algebra generated by C? It's actually rather difficult to do. The only way to do it is to find some other sigma-algebra. If you want to show that something isn't in the sigma-algebra generated by C, you have to find some sigma-algebra containing C that doesn't have U in it. And that's often quite a tricky proposition. So I'll just put a comment on that. Let E be a subset of X, then it may be hard to show that E is not an element of sigma X of C. Usually, you need to find some sigma-algebra and we'll see some examples of that. So, given that you probably don't know exactly what sigma X of C is at a given time, but someone gives you a set and says, is it in there? Then, of course, well, if you'd like to just take F to be sigma X of C, you don't know exactly what that is. But maybe you can at least find a bigger sigma-algebra. And we'll see some examples of this in a bit, where you take some bigger sigma-algebra and you establish that E isn't in that, and then you're home. You know that it can't be in the sigma-algebra generated by C either. Right. A bit of abstraction is quite useful. Given C1 and C2 contained in P of X, then and you want to compare the sigma-algebras they generate. You've got two collections, perhaps completely different collections. You want to compare the sigma-algebra they generate. Then the sigma-algebra on X generated by C1 is contained in the sigma-algebra on X generated by C2, if and only if you can establish that just C1 is a subset of the sigma-algebra in X contained in C2. one way round is obvious because this sigma x of C1 has got C1 in it. So if you've got the first one, you've definitely got the second one. You've got the second one, if C1's a subset of sigma x of C2, then this sigma x of C2 is a sigma algebra, which has got C1 as a subcollection. And we know that sigma x of C1 is the minimum one that does that. So you deduce from what I said above, just from the definition, or from the comments after the definition, that if C1's a subset of a sigma algebra, then so is the sigma algebra it generates. So quite often you've got two completely different collections of sets, and it so happens that they generate the same sigma algebra. How do you check that they generate the same sigma algebra? Well, you normally have to do, it's normally very difficult to establish what sigma algebra either of them generate. But even though you can't figure out which sigma algebra they generate, you can still figure out they generate the same sigma algebra as long as you can prove the two inclusions. So we also have I've got to make a new page. Sigma x of C1 equals sigma x of C2 if and only if each collection is contained in the sigma algebra contained in the other, generated by the other. And that's usually easier to establish. And I'll just explain an example of that. For example, it's a standard fact, and if you've never seen it, then the proof of an exercise, that every open set in the real line is a union, is a countable union, is a union of a sequence of open intervals. I won't even insist that it's every open subset of R, perhaps not empty would be safer. Go for not empty. Is a union of some sequence of open intervals. So the typical non-empty open subset of R always looks like this. If you allow, I don't particularly want to allow empty open intervals, and that's why I wanted to insist that U was not empty. But there are various alternative ways of saying it. Anyway, this is a standard fact that you can quote, but the proof is an exercise. If you have never seen it. actually is an awfully common mistake that I get people telling me that open sets have to be open intervals. And that's obviously not true, right? You just take two open intervals that don't overlap, and their union is no longer an open interval. So there's a difference between them. However, you can look at these two collections. So you set Tor to be equal to U contained in R, U is open in R, that's the usual topology. And let's call C the collection of all open intervals A, B. A, B in R with A less than B. Then C is a subset of Tor. So it's obvious, or you can use what I said before, that the sigma algebra on R generated by C, the open intervals, is a subset of the sigma algebra on R generated by the open sets. Now I'm going to tell you what this sigma algebra is in a moment. This is the so-called Borel set. It's a pretty abstract thing, the Borel set, and we'll talk about it in more detail in a moment. But at the moment, you don't know what it is, but you've managed to show that the sigma algebra generated by the open intervals is a subset of the sigma algebra generated by the open sets. But the other way around is true as well. Again, what I've got to establish now is that every open set is in the sigma algebra generated by the open intervals. Even though I don't know exactly what that sigma algebra is, as long as I can show that the open sets are in it, we'll have established equality. So we prove equality by showing that all open sets are in the sigma algebra generated by this collection of open intervals, so that the sigma algebra generated by Tor will also be a subset of that. I hope you can tell the difference between my Tors and my curly Cs. If not, ask. Okay, to see this, let U be in Tor. We'll treat the empty set as a special case. Every sigma algebra has got the empty set. Now I've gone wrong, right? I'm trying to show this in sigma R of C, not Tor. Otherwise, it's a union of a sequence of intervals. Okay, but now those open intervals are in C, so they're in the sigma algebra generated by C. But the sigma algebra generated by C is closed uncountable union, so the union has been the sigma algebra generated by C. So this is a union of sets in the sigma algebra Well, actually, they're set in C, but if they're in C, they're also in that sigma algebra. That's closure under countable unions. We did that for any U now in Tor. So we're now done. We now have that Tor is a subset of sigma x of C. So the apparently bigger sigma algebra has to be contained in that one as well. You've got both inclusion, so equality follows. Now, this is the remarkable power of abstraction. We really don't know what sets are in those sigma algebras, but we managed to establish that they're the same, just using the power of abstract mathematics. And I think that's a rather remarkable method. And it's a method that comes up again and again in measure theory, far beyond the measure theory we're going to have time for in this module. Any questions about that proof? Okay, well, I'll put some more question sheets for you to try out for yourself of a similar kind. I'm now going to define the Borel sets. I'm focused on the Borel sets in the real line, but you could also do this in any topological space. So we do exactly what we just did, and we get the sigma algebra we just looked at, only now we give it a name. We call them the Borel sets. It's a sigma algebra on R generated by the collection of open sets. So this is as discussed above. And the sets in there are called the Borel sets. So there's an awful lot of Borel sets, as we're going to see in a moment. And it's rather hard to show that you've got something that isn't a Borel set. So we'll come on to that a bit later. But there really are some non-Borel sets around. And we'll be using the axiom of choice to construct something that's very much not a Borel set a bit later, a so-called Vitali set. But let's have a look at some sets which do have to be Borel sets. Okay? Every open set has to be a Borel set because, obviously, Tor is a subset of the sigma algebra it generates. So every open set is a Borel set. But the collection of Borel sets is a sigma algebra. So what can you do to tell me some more things that must be Borel sets? Because if you've got some Borel sets, you can apply our axioms to find some more Borel sets. And then you can apply some axioms to find some more Borel sets. So who can tell me some more things that must be Borel sets?
Closed sets.
Closed sets must be Borel sets. So that's taking complements. Closed sets are also Borel sets. What's the easiest, smallest interesting closed set one can have?
A point.
Point, I think. In particular, single point sets of Borel sets. So they're all Borel sets. So what next? What other interesting sets could you immediately see must be Borel sets, given it's a sigma-algebra? Someone else tell me something. Yeah, so countable unions of stuff we've got so far. So that gives me, well, the open sets you don't get anything new. So countable unions of open sets are open already. But countable unions of closed sets are interesting. So looking at countable unions, countable unions of closed sets, and there's an awful lot of those. Countable unions of closed sets are called F sigma sets. F being a typical letter for a closed set, and sigma somehow representing the fact that you're going to add them together, not really the union, but sigma is for some in some way. What other kind of set that, oh yeah, in particular, countable sets themselves are F sigma sets. All countable subsets, all countable sets, well, all countable subsets of our Borel sets. For example, Q. Taking the complement again, R take away Q is also a Borel set. So a set of all irrational numbers is another Borel set. These were sets that were regarded as quite bad in second year mathematical analysis, and then now you have to say that they're relatively good because they're Borel sets. What do you think the complement of an F sigma set is? The complement of a countable union of closed sets. The complements of F sigma sets are the kind of set we met before, earlier on. Think about it. What does the Morgan law do to when you want to take the complement of a countable union of closed sets? You're going to end up with countable intersection of open sets. You're going to get countable intersection of open sets because you get the intersection of the complements. And we already met that. And they're the G delta sets. Which we discussed earlier. That's the countable intersection of open sets. Right, so we've got a lot of Borel sets. We haven't actually established any non-Borel sets, and that's a much harder thing to do. Well, we'll see how to do it with the acting choice in a bit, but not just yet. But that brings us to the end of this section. I thought I'd see if anybody's got any questions about sigma-algebras generated by collections. There are some easy things you can do here. I'll put them on a question sheet. Things like if you take the closed sets in R, they generate the Borel sets. That's very, very quick. But also, if you take things like the half-open intervals in the real line, you can prove that they are Borel sets and they generate the Borel sets again. So there are lots of different ways to generate the Borel sets. And depending on which setting you're in, you'll find which ones you want in order to prove the theorem you're dealing with. Okay, so that brings us to the end of that section.